let me welcome everybody. Good morning, good afternoon, good evening, depending on where you are located. And thanks for joining this event of the networking channel. The topic of the event, as you've seen, is underwater communications and networking. We have four very well-known researchers active in the field. The panel moderator is Professor Michele Zorzi from the University of Padova. Michele is very well known in the field. He is a full professor now in Padova. He has been previously in Ferrara at University of San Diego, at Politecnico di Milano in Italy. And he has been very active in general in the field of wireless communications and networking. So today he will guide us through this exciting field of increasing relevance, which is underwater communication and networking. And Michele, the floor is yours. I let you introduce our other panelists because you know them much better than me. One thing for the audience, please write your questions either on the chat or on the Q&A, and we will pick your questions at the end of the panel. So, Michele, the floor is yours.
Okay, thank you, Marco. Thanks a lot. And hello, everyone. Thanks for coming. So as Marco said, we have a very exciting topic to talk about today, which is the topic of underwater communications and networks. And what I hope you'll get at the end of this hour is a sense of how large and how diverse this field is. It's not just about closing the link underwater, but there's much more to it. And so we have an outstanding panel with three people in addition to myself who are very well known in this area. So Milica Stojanovic, she's an old-timer in this community. She made very early contributions and continued to do so until now and beyond. So she's a professor at Northeastern University, and she will guide us through some of the issues related to physical layer and the propagation underwater. Costas Pelekanakis, so he's also quite an old-timer. He has more than 20 years experience. He went around, so he was part of very well-known groups worldwide in Singapore, then at NATO Center in La Spezia, and then now he's at TNO in the Netherlands. So he's very much into experimentation and standardization, so that's what he will talk about. Filippo is the child of the panel. So he's young and energetic. So he is also a professor at the University of Padova, my colleague. And he guides a very good team of young researchers working in this area, including also device development and low-cost hardware. And so he'll talk about that, and I will cover some topics in protocol design and networking issues related to what the others will say. So let's jump right into it. And so the order will be Milica talking about acoustic communications and physical layer, then me talking about networks, then Filippo talking about devices, and then Costas talking about standardization and experiments. So Milica, the floor is yours.
Well, thank you, Michele, and not thank you. I don't know how to feel about being introduced as an old. And I noticed that you've
old-timer. It's in a positive way.
There was a pause between the two words. Anyways, thank you very much, and thank you all for joining. Let me share my screen. And let's see how this goes. Oops. Can you see that? Yes, all right. So this is an opening slide that is full of photos, but the way I like to open this story is by trying to figure out, what do people know about the underwater world at all? One thing that we all know is, of course, the story of the Titanic and the movie with Leonardo DiCaprio and all that. And people knew where Titanic sank about for a long time, but it wasn't until the development of some underwater technology that only in '82, you're looking at this blue picture here, a team of engineers from the Woods Hole Oceanographic Institution dispatched a set of vehicles. The big one is Alvin, the little one is Jason. They are remotely operated, and that was the first time that people actually laid eyes on the remains of Titanic. The same team of vehicles was also dispatched on other missions to discover super interesting things. Over here, in this black-blue picture, you're looking at something called a hydrothermal vent. Hydrothermal vents are sources of extra high temperature bubbles and smoke and water at the bottom of the very deep sea. And they have been found to harbor some interesting forms of life, in particular forms of life that have not been known previously. So those are some examples of exciting things that can be found if some technology is in place. And this bottom picture here, of course, is showcasing me and my dog at an experiment involving deployment of an autonomous underwater vehicle under ice. Oops. Sorry. Here we go. So let's take a brief tour into the history. This is another Leonardo, not Leonardo DiCaprio. This is Leonardo da Vinci, who is credited as the first person to have actually figured it out in a way. When I say figured it out, I mean the propagation of sound through the water. He may not have been the first, but he was the first who wrote about it. And you are looking here at the words that he wrote. If you cause your ship to stop and place a head of a long tube in the water and place the outer extremity to your ear, you will hear ships at a great distance from you. And you will hear them because the sound propagates and can travel far and not so fast through the water. Now let's fast forward to the present time. At present time, and what we are talking about here today, we are thinking or dreaming about deployments of quite sophisticated systems, such as this one that is shown in this picture, that could consist of a number of various instruments under the water. Over here, we have some bottom-mounted sensors. Then we have some autonomous vehicles. Then we have things on the surface. They're called surface nodes. They could be buoys floating on the water. And if all the assets under the water can communicate to each other, once you reach the surface, then with a radio link, off you go to the shore. So this is what we are thinking about. Let me do a brief summary. Why do we want to do this? We want to gather data from fixed instruments. We want to coordinate autonomous vehicles and robots under the water. We want to do that wirelessly because the cables that would be tying them otherwise are extremely heavy, they're expensive, and they restrict the motion. Now, how do we do that? Well, one might be tempted to think about radio waves. Unfortunately, they do not propagate through water. They have very high attenuation. The choices that remain are the optical signals and the acoustic signals, the sound. The optical signals do propagate through the water. They do so best in the blue-green region where there is the least absorption. This is why the ocean appears to be blue to us. But they travel over short distances only, let's say about 100 meters. And depending on the kind of devices that are used, they may be associated with pointing precision, such as with lasers. That leaves sound or acoustical signals as the only way to transmit information of any considerable lengths over 100 meters. And the acoustics, as Leonardo da Vinci told us, can do that. However, as we shall see, they have a very, very low bandwidth, pitiful compared to what the optical waves offer. What is in the past, or where does this story begin? Somewhere at the end of the World War II in the United States, a system was developed to be used for telephone conversation between submarines. The system operated using analog modulation, single sideband in the 8 to 11 kilohertz, and is maybe even still somewhere in use today. After that, however, we come into the world of DSP technology, and with that, our story begins. DSP enabled people to deploy relatively sophisticated algorithms in small packagings at remote ends, and this is where the signal processing story begins. What is in the future? More signal processing, reliable networking, as Michele will be talking about, and system integration for various sorts of new applications. Let me illustrate to you one picture here. This shows an oil and gas drilling platform in the deep sea. This one is owned by Shell Oil, where it would be really useful if we could have instruments and robots that could go there and autonomously operate to help with certain tasks. Other than the gas and oil industry, fishing industry, offshore fish farming is a big player as potential users of our technology. And then, of course, various other things that have to do with scientific exploration, mapping of the oceans, and so on and so forth. You've all unfortunately heard about the tragedy of the submersible Titan recently, where we've been exposed to the fact that no matter what you do, people will want to go and play under the water as well. The words that you are looking at on this slide are excerpts from internet, where I searched for some information on the value of the underwater acoustic communication market. Today, you see $3.5 billion with a fairly good projected growth rate. And if Google is to be trusted, and of course there's nobody else, it says that the key trends in the future include advancement in signal processing and the development of sophisticated acoustic modems. Acoustic modems is maybe an old word, but we still use that to describe devices that perform signal processing for closing the link for communicating under the water. Let me now go into the fundamentals of how the whole thing works. You're looking here at two pictures, the path loss and the ambient noise. These two things are the main things that determine what matters for communication, and that is the signal to noise ratio that you have at the receiving end. The path loss, or the attenuation, is shown here as a function of frequency in decibels per kilometer. And as you can see, it's a horrendous amount of path loss, meaning that we are condemned to live in this red circle here where the path loss might be tolerable. But as you see on the bottom axis, we are therefore condemned to very low frequencies. The loss occurs because of transfer of acoustical energy into heat. The picture on the right is showing the noise power spectral density, and maybe you don't want to pay too much attention to the various curves. They differ by the wind speed or the shipping activity. Shipping causes noise, ambient background noise. Wind causes waves, waves break, bubbles are injected into the water, bubbles burst, and that's what causes acoustic noise. What I want you to notice here is that this power spectral density more or less goes down. So it's not flat. The noise that we have is not white. It may be Gaussian, but this tells us that we should be careful about making conclusions that were otherwise made for white Gaussian noise. Now, when you put the two together, the path loss and the noise, you can come up with a picture that looks like this. This picture is showing essentially the signal to noise ratio that you can expect in a small range of frequencies around the frequency that is shown on the bottom axis. Let's look at the link that is 100 kilometers long, for instance, this one that I'm tracing here. Obviously, at this point, you have the maximum signal to noise ratio. That is where you would want to sit. You go down a little ways from that, say 3 dB down, and the two arrows are pointing to your useful bandwidth. So you see, about a kilohertz at a kilohertz. That is not a narrowband system according to the strict definition of what narrowband means. And this is what I mean by the words underwater acoustic equals ultra wideband The bandwidth in absolute numbers could be very small, but it is not negligible with respect to the center frequency. And that fact alone has serious implications on the design of signal processing methods that are to be used. Now, as the distance decreases, these curves stack up like that. You see that you have more bandwidth, but you still are essentially remaining broadband. The picture on the right is a collection of the optimal points, and it shows the optimal center frequency as a function of distance. You see that the farther you go, the lower the frequency, and therefore the bandwidth will be lower as well. So if you were to put this into a quick summary and ask yourself, all right, what's the difference between radio systems as we know them and acoustic systems? Here you have two axes, the radio frequency axis and the acoustic frequency axis. Along the radio frequency axis, our typical systems that are in use today that we have in our pockets might be working around some gigahertz, and they might have a huge bandwidth, a megahertz bandwidth, but megahertz are negligible compared to gigahertz. In contrast, the acoustic frequency axis is shown here, and as I mentioned, you might be sitting around some kilohertz with a bandwidth of some kilohertz. So the bandwidth is not negligible to the center frequency. Plainly put, radio frequencies are like a Porsche flying across an Italian autostrada. Acoustic frequencies are like elephants crossing a river slowly. They'll get to the other side, but it's not going to be fast. Now, within this limited bandwidth, what do we have? We have a whole lot of different distortions that make our life both difficult, but they also make the signal processing fun. One very distinguishing feature of acoustic communications is the Doppler effect. The Doppler occurs when anything is moving. You are looking here at a little picture showing one vehicle transmitting to either a vehicle that is moving towards or away. A certain frequency, a certain tone, will then be perceived as either having an increased frequency, shortened time, or a lower frequency or dilated time if you want. If you look at the same effect along the frequency axis and you are transmitting a signal that is shown on the upper line, what you might be receiving is the signal that is shown on the lower line. Each frequency component will shift due to Doppler. And the implications of this are serious on frequency and phase synchronization, both up front at the input to the receiver and for fine tracking later. Another thing that occurs in this channel is multipath propagation. Multipath propagation is a very serious problem in the acoustic channel. And if you want to talk about the mechanisms of multipath formation, you might delve deep into the issue of whether you are in shallow water. Here you are looking at a cross-section of the ocean bottom from the land to the abyssal plain at many kilometers deep. If you are in the shallow water, multipath forms pretty much by reflections of the surface, of the bottom, of the surface, of the bottom. If you are in very deep water, the situation is slightly different because, as it turns out, the speed of propagation, the sound speed, changes with depth. As a result, if you put a transmitter at a certain depth, the depth is shown this way, there will be waves that are propagating towards the receiver that will never reach either surface or the bottom because they are too far, but will nonetheless bend and effectively create multipath at the receiver end. The reason why they bend is pretty much by repeated Snell's law, because the waves of sound tend to always get back to the point where the speed of propagation is minimal. They're lazy, so to speak. As a result, you have a multipath composition that might look like that, which creates frequency selectivity in your signal. Some frequencies are favored, some frequencies are not favored, and these are only the frequencies within your bandwidth, nothing to do with the big attenuation that I spoke about before. So multipath can be pretty bad, as in you could have multipath delay spreading that is maybe even 100 times the inverse of the bandwidth. that is very long and has to be taken care of through the process of equalization. Finally, there is time variation that appears to us to be random, sort of like fading. What you are looking at here are two pictures corresponding to two different underwater channels, each of them showing a collection of impulse responses of the channel along the delay axis as the time evolves. And you can obviously see that there is some time variation and that maybe it has no sense. In other words, it appears to us as random. At this moment, we still do not have any standardized models that would provide a statistical description of these apparently random variations. We're trying to work on that. So what do we do to fight these channels? We do a lot of silly things. But the bottom line is, at least on the physical layer, we talk about propagation modeling, signal processing, and ties into the networking algorithms. We talk about frequency synchronization, using the arrays to improve the communication, and finally, making the network protocols comply with this not so nice nature of the channel. Here is a summary of many years of work on signal processing for closing the link using single carrier modulations. This may look too complicated to many of you. For those of you who were working in the area, it may look relatively simple. The basic structure of the receiver that we are using is shown here. There is a combiner up front that takes spatially distinct inputs, so array inputs, combines them into a certain number of outputs, and these outputs are subsequently fed into the rest of the system, which is essentially a multi-channel equalizer. The equalizer consists of some feed-forward filters, a sum, and then a feedback section. This type of equalizer is known as the decision feedback equalizer. It is not the optimal thing to do, but it is the only thing that is computationally sensible from the viewpoint of the length of the intersymbol interference that this channel experiences. This inset shows an example of performance of this receiver structure on a channel that was 50 nautical miles long, operating at 1 kilohertz. Obviously, this is 8 PSK modulation, and it seems to be working rather well. The key point here is that the entire receiver structure operates as dictated by an adaptive algorithm, and this adaptive algorithm does two things. It adapts the coefficients of the filters, but also adapts a phase tracking device, a phase-locked loop, that is responsible for holding in check that Doppler effect that I was talking about. This receiver structure was implemented in the Woods Hole Oceanographic Institution's acoustic modem, the so-called micro modem. You can look this up and see more technical details about the implementation. And the little list in green over here is showing various examples of where this modem was deployed and what are some pertinent numbers. For instance, if you are going over a medium range channel, let's say between 1 and 10 kilometers, you might reach up to 10 kilobits per second. And that is what for us would constitute super high transmission rates. If you go over longer and longer distances, the data rate given here in kilobits per second drops. Here is an interesting one. Basin scale means halfway around the globe. We were able to do that too at all of the 10 bits per second. Anyways, it's very interesting how to design these things and prove that they work using real data. After the initial work on single carrier modulation, our research has moved into the area of multi-carrier modulation and OFDM, orthogonal frequency division multiplexing, where the approach to treating the frequency selectivity and multipath distortion is slightly different. It is a preemptive approach that goes on the transmit side, looks at the entire bandwidth where the channel is frequency selective. It goes up and down this transfer function of the channel, and it chops the bandwidth into many small chunks, assigns a carrier to each small chunk, and proceeds to transmit. On the receive side, every input element of the array is processed by an FFT block, which is essentially a demodulator. Combining is then performed, and the loop is finally closed. OFDM has many positive advantages listed here with little pluses. It has very simple FFT equalization. You basically equalize only per each subchannel. It is scalable with bandwidth. You want to change the design of your system, you just throw in more carriers. It allows for adaptive modulation, multi-input, multi-output processing, differentially coherent detection. It does have two disadvantages. One is the high peak to average power ratio, which is present in radio systems as well. And the other is high sensitivity to Doppler. If there is Doppler present in this channel, each of the frequency bins will slip, and you'll have a big problem on the receive side. We have, however,
Okay, thanks.
Say that again.
Yeah, thank you, Milica, for this very informative overview of the physical layer.
There you go.
So let me move to the networking part here. So here's the presentation. Okay, so the vision we have is the Internet of Underwater Things. That's one thing that we want to realize. The second is, can we make Wi-Fi or cellular work underwater? After all, 2/3 of the Earth are covered by water. Can we enjoy there what we enjoy on land and we are used to? So underwater communication has been around for some time, for some decades, in fact, mostly focusing on physical layer, as Milica was summarizing. There is a lot of issues that have been addressed and still are being addressed. But then networking has also emerged as an important topic relatively recently. And clearly, from the numbers Milica was mentioning, what we can do in terrestrial water communication is much, much more than what we can do underwater, both numerically and also qualitatively. But the question is, can this gap be reduced, at least qualitatively? Now, the main features of acoustic communications is the rough propagation channel, as Milica was saying. So it's providing robustness, predictable quality, data rate, success rate is quite challenging. So that needs to be taken into account. The other big thing that she didn't mention is that the propagation speed of sound is very, very much slower in water than the propagation speed of electromagnetic waves. So if we could use RF or optics underwater, we could travel at this, hundreds of thousands of kilometers per second, whereas with sound, only 1.5 kilometers per second. And so this means, from the point of view of delays, latency, but also how protocols are designed and can work, a lot of different effects compared to what we're used to. Essentially, in RF communications, propagation can be assumed to be instantaneous, except for maybe satellite communications. Here, we cannot make that assumption, meaning the propagation time may be even bigger than the packet duration or whatever time scale you use in your protocol. And that is a very significant difference, both because we need to design protocols around this and because when you optimize a system, you cannot neglect the time dimension. You have to factor that into the model explicitly, and this makes the model more complex and more difficult to optimize. Other features, expensive equipment. Experimenting in the water is very, very expensive and difficult and requires specialized skills. And also there are some specific effects not encountered in classical networks. So my favorite is this distance-dependent bandwidth that Milica was mentioning, which has some relevance to routing. So when it comes to acoustic propagation, we need to design our network around these special features. For example, the thing I mentioned about long delays makes ARQ, so recovery of errors by retransmission, not always convenient. Forward error correction also is a bit tricky because bandwidth efficiency will suffer and we don't have that much bandwidth. And so this is something that we need to take into account. And so there are things that lead us to different design choices. And this, there is a lot of rethinking and redesigning and adaptation that needs to be done here. And a lot of questions that may need to be asked. For example, if you have a MAC protocol, typically if you have two nodes sending together, then you have a collision and you lose all packets. That's what happens in radio. But in underwater, if you have different distances, the time difference between the two may actually make the two packets to reach the receiver at different times, even though they were sent at the same time. And so this is what I was saying earlier. Like you need to factor in explicitly the timing relationship, and you can schedule effectively, even though the problem becomes more difficult because you have, a space-time optimization you need to do. The other thing that is interesting from a networking perspective, so Milica mentioned the different technologies you may have. So if you compare them in terms of bit rate they can achieve and range they can cover, this is what you obtain. Different colors are for different technologies. And clearly you can see that if you prefer high bit rate at low distance, then you may go with optics or even RF in some cases. If instead you want long range and you're willing to accept a lower bit rate, then you go for acoustic. And so there's no unique solution for all applications, and you can choose or switch between technologies according to what you need and what you prefer, or you can even think of using these technologies together in a synergistic fashion, and there are examples for that. And so this is a relatively new frontier, which is called multimodal communication and networks, which is being studied. And so we can expect some promising results coming out of these studies. Now, to conclude, so even higher layers. So we mentioned the MAC layer, which is the one which is maybe most obviously related to the delay issue. Now, if you think of routing, again, the distance-dependent bandwidth. So if I have to choose between a long hop with a smaller bandwidth or multiple shorter hops which then have bigger bandwidth, which one would I prefer? So that's a valid question that needs to be answered. And I should observe that, if you're in wireless radio research, ad hoc sensor networks, there are gazillions protocols for routing in that area. In underwater, we're still using mostly flooding-based protocols, which are, very primitive in a way. But, all the difficulties make this actually a viable choice, even though we have, a lot of fancy protocols that were proposed in other areas. Now, transport layer is another area where delays and losses may actually kill your protocol. So TCP is not well matched to this environment. And so we need to do something about that, also because TCP has a lot of overhead, which we cannot afford in this area. And then there are other topics that are being mostly overlooked until recently, like security, for example. And then what is the effect of mobility? How can localize? These are all things that they're routinely done in wireless radio. And here, they start to be considered and solutions start to emerge. So to conclude, my point is that using acoustic links, makes challenges that we need to resolve not only at the physical layer, but the whole protocol stack should contribute to solving these issues in the best possible way. Protocols need to be adapted or maybe even redesigned around different constraints, which is exciting for those of us who do research in this area. TCP/IP is too costly in terms of overhead, so how should we change it? Also, the community in this area is quite small if you compare it with the wireless radio community, and maybe more coordination and more promotion of the work that can be done here, trying to get other people involved, would be a very good idea. And the standards in this case, of course, help, as data sets may help. So I know Milica is involved in an effort to collect channel models and to make them available so that the community can use them for experimentation. So that's a very good thing that we can do to promote this kind of area. And so with that, I leave it to Filippo talking about devices and low-cost modems.
Thank you, Michele. So here I'm talking about underwater acoustic modems in general that have been used since decades, mainly in oil and gas and military applications, or in offshore applications like tsunami predictions and coastal monitoring. The main characteristics of most of these devices is that they, in offshore application, they need to reach high power, they need to reach long range, so they have a high power transmission. They are offshore, you know, they have to be placed in deep water, so deep water rated devices up to thousands of meters. And even if they have a limited bandwidth, they still have quite sophisticated and expensive receiver to try not to waste any bits. So they aim to reach some kilobits per second in some good channels, also some tens or hundreds of kilobits per second, although in most of the cases it's few kilobits per second or even less, but still. And all of this results in quite expensive devices that you won't go to the supermarket to purchase yourself. However, having acoustic modems for everyday life application could be quite handy for some circumstances. For example, micro AUV, micro underwater vehicles, swarm coordination, sensors for pollution detections, diver-to-diver communication for having divers performing coordinating missions. And now we have the issue of fish traps like lobsters and crab traps that are deployed through ropes anchored to a buoy. And this rope cause lots of frequent entanglement with marine mammals that then causes a risk of their lives. So roopless fish trap could really help in this way. Moreover, there are lots of students playing with underwater vehicles because now they start to 10 years ago they started selling low-cost underwater vehicles. So there are lots of student associations that are playing with these vehicles, and they do not have a lot of acoustic modems to use with the vehicle. And this is limiting a lot the research, as underwater vehicles might cost less than acoustic modems. So we need to lower the cost, we need to change the working domain from defense and offshore to something that looks more like this, where we can provide to students and researchers without a big wallet a way to experiment on underwater acoustic communication. First question to cut the cost is why are they so expensive? First of all, the transducer itself, that is the underwater antenna. We basically use acoustic transducer that are nothing less than an underwater speaker and an underwater microphone. They can cost more than $2,000, and they support high power transmission, rated for thousands of meters depth, and calibrated. The calibration is a process that costs a lot. So cutting the cost of this transducer can be very helpful. The high power electronics for hundreds of watts transmission might not be needed by researchers and students. And casing for deep rated for thousands of meters, it's also something that might not be of interest if they want to deploy it in a river or in a shallow water lake. So the commercial models, the legacy commercial models, with legacy I'm not saying that they are bad, they are very good actually, and they are mostly used for offshore deployments. Here it's a list, and all of them have the characteristics of be able to communicate up to a range of some kilometers and have a rate that can be up to few tens of kilobits per second in good channel condition. If the channel is bad, it will be less than 1 kilobit per second, but still, this is kind of the characteristics that acoustic modems have. This is just a short list, it's not complete, but to give a quick overview. So cut the cost. Instead of using calibrated transducer, we can use not calibrated hydrophones able to transmit low power, or make the transducer ourselves. This will be not certified, not calibrated, probably not as good as a transducer that costs 2,000 euro, but with 100 euro or even less, you can make your own. Low power electronics, using off-the-shelf components for audios, or making your own low power circuit. And maybe you don't need deep rated casing, so either OEM, so without the casing, you just put the transducer with a long cable in the water, or you try to case it yourself somehow. If you need to put it a few meters under the water, IP, very good IP rated enclosure, maybe filled with some gel might be enough. And in the case you are a company, change the business model for selling the modems, because forgot to say why one of the reasons why the acoustic modems are that expensive is that there are not a lot of people that are really buying them. So they don't sell hundreds of thousands of devices per company, but probably a few hundreds per year, and they need to give the food to their family anyway. Instead, if we change the business model, having a lot of devices sold, taking this mainstream, maybe we can make it. Here are again a short list of the some low-cost acoustic modems. This is not really a short list, this is quite complete. Here it's the new thing is that until 10 years ago, we only had research acoustic, low-cost acoustic modems. Now there start to be some commercial acoustic, low-cost acoustic modem available. These cost less than 1/5 of the high-performance one I mentioned before. You see the range here is usually less than 1 kilometer, and the rate is a few hundreds of bits per second. But this might be enough for students and researchers to start with. Now, what do our researchers need as a platform for making experimentation? Usually, it needs something flexible to experiment with new waveforms and routing algorithm. Usually, this comes. The solution of this is using a software-defined modems and a software-defined network. Here, it's really nothing that new, again, because software-defined modem exists since a lot of years. There are a lot of research modems. Every large research institute developed its own research modem, like the NILUS from TNO and FFI. Milica, I'm sure, has developed many at MIT and Northeastern, and use the one from VOI. Evologics and some Nero are selling software-defined modems as well, although they are not super cheap. The main issue of these devices is that either they are not commercially available because they are being developed by a research institute for its own research purposes, or are quite expensive, and either you purchase them in the context of a big funded project or a small research group might not take them. With software-defined network, this is easier because there is a lot of choice in the market. Some of them are commercial, some of them are open source. So in our case, during our research project, we decided to develop our own software-defined acoustic modem with the goal of making it low cost with mainstream devices like Raspberry Pi is a processing unit, and then we used a very powerful data acquisition system for Raspberry Pi that is nothing else than a sound card sampling at 192 kilohertz. On top of this, we develop our own electronics for pre-amplifying the received signal and amplify the transmitted signal with a transmission and reception switch. Given that all the software is running in a Raspberry, we can also use software-defined radios on top of the software-defined modems, having also possibility to use it in a multi-hop network. After we developed this in the Restart Aquasmart project funded by the Italian PNRR and the MODA project funded by the Italian Navy, some of the partners of these projects asked us to provide them with the same equipment, and they told us that they wanted to purchase the same equipment. So given that we were a university that cannot sell modems, we decided to spin off and create SubSeaPulse, that is a spin-off company of the University of Padova, to make a commercial version of this modem that is one of the outcome of the Aquasmart project and the MODA project from the Italian, founded by Italy. And so now we have this modem available that we think might be quite handy for researchers. Has been tested in quite different scenarios from our students and our student association, and also by the Italian Navy. So depending on the transducer you plug, if you put the transducer that is, let's remember, the underwater antenna, the one you make yourself, it will fit very well in the river scenarios with the gondola you see on top. If you instead use a very good transducer, this won't be anymore a low-cost modem, but will fit well offshore scenarios, as well as the performance there were quite good. And so I conclude my presentation on devices for experimentation for underwater acoustics. This modem also want to be to support some of the standards that Costas will talk about.
Thanks a lot, Filippo. Costas, now the floor is yours.
Thank you, Michele. Let me see. You can see my screen. Excellent. Okay, so okay, let me start by the vision that Milica already showed in her first slide about underwater networking. This is what we would like to achieve as researchers and engineers, an underwater network consisting of heterogeneous assets, bottom mountain nodes, AUVs going around, divers, submarines, and all these messages that they want to communicate, they need to be also relayed on the above the sea surface using gateway buoys to ships, source stations, and even satellites. But the issue here is that one company alone cannot deliver this vision. This is a vision that will be delivered by different companies selling different products, and they need to interoperate. And in order to interoperate, you need communication standards, because you need to ensure that all the devices will speak the same language. So if we see what's happening in the terrestrial world, we are users as individuals. We are very familiar with communication standards in our daily lives. Almost every one of us uses Wi-Fi, Bluetooth, 5G in our cellular, in our cell phones. Also in the optical domain, terrestrial optical domain, you have standards for indoor light communications, extending the Wi-Fi and to Li-Fi. You have also satellite links where you have high-speed communications between the Earth and satellites. And the million-dollar question is, could we use these existing standards in the underwater domain? And the short answer, of course, is no, because of these fundamental differences that the underwater environment, either acoustics or optical, has with the corresponding terrestrial one. So we need to go with the bottom-up approach in order to develop our own standards. And here's the situation about what is happening. What is the communications? What are the communication standards that exist underwater? For acoustic communications, you have mainly two key efforts coming from NATO. One standard is called Genus. It's named after the Roman god of transitions and gateways and portals. And the second one is called IFS, which is IFS means identification of friendly submarines. And this is a military standard and it's classified, while Genus is open to everyone. In the optical communications domain, you have absolutely no standards. So definitely there is a capability gap that needs to be bridged. So what is Genus? Genus is the first digital underwater communication standard. This started from a combined effort of the NATO Center for Maritime Research and Experimentation and academia and industry. After many years of research and development and experimentation, it promulgated in March 2017. And the official name of this standard is Standard 4748, and the technical description is in this technical document ANEP 87, which can be downloaded by the NATO Standardization Office website. So as I said, it's open free, and it's open and free to use it. And there is a reference implementation. There's a reference implementation of the transmitter and the receiver in this Janus Wiki website. But I forgot to mention that the standard only refers to the transmitter. The receiver is not part of the standard. And this is for a reason. We want to encourage innovation from the industry in order to develop high performance receivers and where they can use them for a competitive advantage. Okay, Genus focuses on the physical layer of the open systems interconnection, where with some rudimentary medium access control. The waveform basically, so the Janus is a way to map bits into a waveform, and the waveform is a frequency hopping binary shift keying type of modulation, which is resilient enough to multipath and Doppler. All the parameters of the waveform are related to the center frequency. When you define the center frequency, then the bandwidth and the chip rate are immediately defined. Currently, there are 5 bands which are available, and in order to accommodate different hardware and also to avoid interfering with other well-used products like sonar, the most typical band is band A, which it has the carrier frequency is 11.5 kilohertz and the bandwidth is 4 kilohertz. Here in the bottom right, you see a sketch of the signal in the frequency time plane. You have 3 optional wake-up tones that basically we use them in order to wake up the modem if it is in a sleeping mode. You have a silent period after for 400 milliseconds, and then the Genus baseline packet starts. Regarding the MAC protocol of Xenus, it allows you to reserve the channel for a fixed amount of time. And also, Xenus allows you to do carrier sensing with backoff, so that you avoid any interference if there is an ongoing transmission from another hardware. So the whole purpose of Xenus is to also is to break the interoperability back in the interoperability gap, but also to coexist with proprietary solutions. So Xenus has been extensively tested in various configurations, typically with the band A, which results in 80 bits per second. You have the typical operational scenarios are on the left side. You have a direct link between a surface unit and the submarine. This is a point-to-point link, but also you may have an indirect link between a surface unit and submarine through a relay, and that relay is a buoy. Typical distances that we have tested Xenus is between 1 and 5 kilometers, depending on the propagation conditions. Xenus has been used in several applications, and here I describe two that are very well, let's say, accepted by the operational community, and the people are very enthusiastic when they talk about it. On the left side, you see an application about search and rescue of submarines. You see a map where the Navy officer sees on her screen, and with the pink arrow you see the geographic positions of surface vessels. But here you see the point where a submarine basically transmits its distress signal using Xenus. And here you see by pressing the button, you see the geographic position of the submarine. And also in the pink box, you see relevant information about the conditions, apart from the geographic positions, the oxygen, the temperature, the survivors, which are in the submarine. And this information is according to the doctrine of search and rescue for submarines. On the right side, you see a screen on board the vessel that displays a message exchange between the submarine and the surface unit. This is called, it's a chat interface, and it's called WhatsApp. No wonder why. This is a way to interact with submarine in real time, configure, basically dictate operational conditions, but even also to have recreational chatting about if the weather is good, or if something is happening in daily life. So this is also a very well, let's say, accepted application of Xenus. So Xenus. So what we have, Xenus is not the end of this interoperability journey, but it's just the beginning. What we have now, we have Xenus supporting low-rate communications with a rudimentary MAC layer. You can use Xenus for command and control of vehicles, live chatting, transmitting geographical position, or even to send small bytes. However, we need more than this, and we effectively need high rate adaptive networking, meaning that we need to have a flexible communication stack from the physical layer to the network layer. We need at the physical layer adaptation in the data rates in order to serve various application requirements. We need adaptation in the network topology. We need nodes that are joining and living in an ad hoc fashion. We need multi-hop routing. So all these things are something that we need to address. These are capability gaps that we need to address. And this is something that has been partially addressed by an effort that started in 2018, where you have 5 nations, 5 European nations, Netherlands, Norway, Germany, Sweden, and Finland. They teamed together in order to create this SALSA communications protocol. And the goal of this protocol is to scale up network capability and also standardize network protocol stack. At the physical layer, you have, apart from Genus, which is used for first contact and handshaking, you have a high-speed waveform technology, which is called FRSS, Frequency Repetition Spread Spectrum. And effectively, this is a multi-carrier modulation technique and uses adaptive equalization at the receiver. Pretty much what Milica described in her slides about equalization. At the network layer, you have a dynamic addressing of nodes and multi-hop routing. And this network stack has been extensively tested in real-time maritime conditions between Germany and Norway.
Okay, Costas, thank you very much. I think we have reached our time limit. So
Okay.
it was, challenging to pack all this information in just 1 hour. I hope that, what we were able to tell everybody during this time was useful and could be followed. Then we'll be happy to also take offline questions if anyone is interested. You can find their contact information either on the web or on the network channel website. To you, Marco.
Yes, thank you very much. Very, very interesting. I learned a lot of things. Let me particularly thank Milica for taking care of the written questions, providing written answers. If someone has more questions, please use the Slack channel or contact directly one of the speakers of today. And let me thank very much all of our panelists and Michele for putting this together. This is the last event before the summer break. So information about future events of the networking channel will be broadcasted through internet advertisements and so on. So thanks very much for joining, and thanks very much for sharing with all of us so much interesting information.
Thank you, Marco,
Thank
for
you.
inviting us.
Thank you very much. And
Bye,
I
everyone.
apologize for going over time.
No, that's fine. That's fine. It's always difficult to stay within the tight boundaries. Thank you very much, everybody.
Okay, thanks again.
Thank you.
Bye-bye.
Thank you. Bye.
Bye-bye.